Okay, guys, I want to give you a quick introduction to a lab we're going to do. Lab in the best way we can do it in the circumstances. So there's a classic lab known as Hooke's Law, and Hooke's Law is going to look at the behavior of a vertically mounted spring. So I've attached a pendulum support. There's a regular spring attached on the top of the support. It's hanging down. There's a hanger, a mass, a pan that holds masses. It's a little platform here, and you slide these slotted masses on. And what Hooke's law does, it looks at the relationship between the amount of mass on the pan and how far the spring stretches. And it's pretty obvious, but the idea behind here, the relationship's pretty obvious, but some of the conclusions drawn from the graphs are important. So obviously, if I put more mass on here, it's going to stretch more. But remember, when we put this mass here, work is being done by work in physics sense being done by gravity. So this mass is being pulled down by a force that's going to displace this thing. So there's work being done. And remember, whenever you do work, there's energy stored. So in this case, we're doing the work, or the gravity's doing work on these masses, causing displacement F times x. But we're storing spring potential energy we talked about the other day. So if I took these masses off, these things would be flying. That spring potential energy would turn into kinetic potential energy. So that's what Hooke's law is really looking at. So I'm going to show you a series of pictures of different trials I did. And what I'm going to do is I'm going to zoom in so you can actually see the trials. Now, this first trial is actually not a trial, it's a reference point. We need to know where the pan is before we start the lab. So when we add masses, we can measure how far it moved. So right now the pan is empty, the mass is 0, and I'm going to zoom in. And I'd like you to try to do this really carefully. And it's easy to just go, oh, 57. But 57 is not a very good measurement, so let's try to be precise here. What I'm suggesting you do is take the bottom of the pan and use the bottom of the pan every time. So I'm doing the best I can. I follow the bottom of the pan over, and I have 56.9. So 56.9 is my reference point. It's my 0 point. And all my measurements I take subsequent to this will be measured relative to 56.9. So let's say it moves down to 58.9. I'm going to say the displacement was 2. 58.9 minus 56.9, it's 2 centimeters. So this, in all of the measurements, are going to be taken back from this 56.9 reference point. And I wrote that on the lab, I think. I set this up before and wrote that down. Now, what I'm going to do is click through a series of pictures and zoom in. I'll quit talking in a minute, but I'm going to zoom in. So this first one has a one mass on here. Each of these masses is 50 grams. So be careful, 50 grams is 0.05 kilograms. And our measurements, so our masses will be in grams. We have to convert that to kilograms so we can turn it to a newton, or turn it into newtons by multiplying by 9.8. And likewise, our measurements will be in centimeters, but we got to convert those to meters. We have to make sure we're in base units. So again, let's just do this first one together. I have 50 grams on here. I fold this over, and this one I would say is about 59. So again, I'm taking the bottom of this fold over, and it's about 59. So the delta in that case would be 59 minus 56.9 centimeters converted to meters, blah, blah, blah. So for each of these slides, hopefully they're all in sequence. I'm going to look ahead, 100 grams, zoom in, you make the measurement. Now, if you need to stop the video, I tried to shoot perfectly horizontal, but I didn't do a very good job on some of these. If you need to stop the video and pause it, then make the measurement, go ahead. I'll do it relatively quickly. You can count. The reason I mentioned each one's 50 is that my last trial I did it long, so if you need to count, go ahead and count. Try to take out the bottom. I didn't line these up very well. I'm going to get my camera level, but do the best you can. You should get this data. This is obviously not a great substitute for reliable. Okay, you can pause the video if you need to. Pause. Video short. 66. Yeah. We can. I think 10 or 11 grams. Oh, you do? Okay. Thank you. 400 or 500 grams. This is 500 grams. So what you're going to do, obviously, is you're going to get this data, and it's kind of following a very good pattern. You'll see when you plot this, it looks really well. When you get into graphical analysis, you'll do a plot. Just pay attention to the axes. It's explained in the lab. The axes are kind of backwards, so just make sure you read the lab. Use graphical analysis, and remember, you're doing this in a group of 1, 2, or 3, I think. We'll talk about it in class. And then just submit one per group. You don't have to submit. Just make sure everybody's name's on it. So that way I know who is in your group. So we're getting close here. 9th or 10th now. That's it. Okay, so that's the last of the trials. So again, what you have there are trials of 50 all the way up to 500 grams. Convert to grams, convert to distances, get them into equations of kilograms, and eventually newtons, and eventually meters, and then make a graph with the best fit line, get the slope of the best fit line, and that means something, and we'll talk about it. Normally we do this in a couple different springs. We have different size springs, and I'll talk about that in the post lab. Okay, so there's your data. Fill out the form, and you should be good to go.